This is the 17th video on single agent search in a course on that. And in this video, we're going to be continuing from last time in the sense that in the last videos, we were looking at the theory and some of the history behind bidirectional search. And what we're going to do today is we're going to start looking at some algorithms for bidirectional search. And there's a number of different algorithms. So what we have is, for instance, I mentioned in a past lecture, we have older algorithms like BS star. And then something that's been more popular recently, and I think this algorithm is covered in the latest version of artificial intelligence, a modern approach, is the algorithm, which meets in the middle. Meet in the middle. And then we're going to get to NBS is what we're going to primarily cover in this lecture. And then in the next video, we're going to look at a body of work, and I'll explain the difference between those. So I'm not going to talk about BS star. BS star is, well, there's some shortcomings in that algorithm, and it makes some assumptions, and we have better algorithms than that now. So this is sort of behind the state of the art, or it is behind the state of the art. in many senses is also behind the state of the art, but I just want to point out a few key features here, because there's some ideas here that were sort of key to be built upon to get some of the better algorithms that we have now. And then NBS is gives us worst case guarantees. And so that's what's interesting about the algorithm. It doesn't use front-to-front information. And again, we'll get to that in the next lecture and maybe talk about a little bit here. There's other algorithms, like, so there's a version, so this is NBS, there's DVCBS, let's see, DVCBS, I think. Yeah, dynamic vertex cover, bidirectional search. And these two algorithms, for instance, are based on the idea of looking at a bidirectional search problem as a vertex graph cover directly. And so NBS basically has a worst case guarantee. DVCBS doesn't have a worst case guarantee, but is trying to be greedy. And so that can give you better performance in practice. And but as I said, we're going to look at the general principle right here. And then, as I said in the next lecture, what we're going to do. So in fact, let me just say, so NBS is near optimal bidirectional search. And what that means, it's near optimal, not in the paths that it finds. So it's both optimal and complete. But so it's not near optimal in the solution that it finds, but it's near optimal in the number of node expansions that it does. And so no more than 2 times the necessary expansions. And that means you give me any other algorithm that takes exactly the same information, and NBS will do no more than 2 times, again with these theoretical caveats, of the necessary expansions, no more than 2 times. Now there may be unnecessary expansions, and NBS may do some of those expansions, or we can give it more information, which is, again, how other algorithms can improve on top of NBS. But this is a nice framework, and it gives us a nice baseline. And so we'll use this as a baseline to understand what's going on here. And but in doing this, NBS as it's formulated can re-expand the same node in both directions. There's some things like that. These can be fixed if you assume the heuristic is consistent. And there's other things like this that can happen. We can add epsilons in, but anyway, I'm not going to talk about most of those details. But what I do, so let me just point out, so that's what we want to talk about primarily here. But just for a point of reference, so sort of falls in the same category. Both NBS and can actually work with inconsistent heuristics. They're still guaranteed to be optimal and complete, which not all other algorithms have that property. And has this really nice guarantee, which I'm not going to go through in full detail here, but it guarantees the frontiers meet. So the forward and the backwards frontiers they meet, and they meet exactly in the middle of the solution cost. Okay, and so that's a really nice property, this guarantee. And what's more is actually we guarantee that no, I mean, this is sort of saying the same thing, no state with cost C star over 2, so a cost greater than C star over 2 will be expanded in either direction. Okay. So MM gives us that guarantee. I'll just show you what MM does, and I can mention briefly why it does it. So MM just uses a priority of a state. Some state n is going to be the max of g plus h of n. And so that should be g of n and 2 times g of n. Okay, so we can write this. If I write it this way, then another way to write this is equal to g of n plus the max of g of n and h of n. Okay, and what we can see here, if we look at this priority function, it says, well, look, if I do know that I'm not going to go past the middle, then for every state that I expand, then I can either use the heuristic to give me an estimate in the other direction, or I can use the cost that I've gone so far as a cost to go estimate. So it uses actually the forward g cost as actually a heuristic, and you can choose to use it as a heuristic, or you can choose to use it in the other direction. And what you can see is if there is a state with cost greater than C star over 2, then g of n plus g of n would be greater than C star. And we can show that actually there is a path that exists from start to goal with cost C star, and therefore we'll always find that cost before that node. So just to show this picture here, we have the start. If there's some node here where the cost is greater than C star over 2, here's the goal. We do know that there does exist some optimal path with cost here of C star. Then what we can see is that the priority of this state, if we call this n, the priority of n has to be greater than C star. Okay. Because 2 times the g cost will be greater than C star. And I use the maximum of g of n and the max of gn plus h of n. Okay. Now, the problem with MM as an algorithm is actually from the theoretical perspective, it does some expansions that are not necessary. And so there's some other pieces we can put together. Those pieces are used in other algorithms. So that's why we're going to cover them with those algorithms in the next lecture. So what we can do now is let's go back to NBS. So that's MM. It's an interesting algorithm in that it got us sort of into this sort of modern view. But notice, or just historically, MM came before the theory of bidirectional search and the theory of necessary node expansions. And so that's why MM actually can expand nodes that are not necessary according to that theory, because we didn't have those tools to analyze MM when it was developed. So what does NBS say? Let's go ahead and move to that. Oh, I should also say there is an algorithm called FMM, which can meet at a fraction, f, and that can be any fraction. And then there's another version of this algorithm that has been developed that instead of explicitly saying a fraction, you can use a policy. And so it uses a policy to decide when to expand each direction, but it's equivalent to meeting at some fractional point in the middle. And anyway, so those are other approaches. But I want to go over NBS here because, as I said, it's somewhat like an equivalent to A star when we are looking at a general admissible algorithm that doesn't know whether a heuristic is consistent or inconsistent. So this is important. NBS doesn't know if the heuristic given to it is consistent or inconsistent. So it's going to have one algorithm that can work both for consistent and inconsistent heuristics. And for that case, we can analyze what happens when it is given a consistent heuristic. As I said, no more than 2 types of the necessary node expansions. And so the argument here, and again, if you haven't looked at the last video talks about how we can model our problem as a vertex cover, is we're going to be thinking and for NBS, we're going to be thinking of our problem as a vertex cover. And when we think of it as a vertex cover, then there's actually an algorithm that exists for finding a vertex cover where you find two states that are not in your vertex cover, and then you basically add both of them to the vertex cover. And so this is an approximation algorithm that is no more than 2 times the size of the minimum vertex cover. And this appeared in a book by Papadimitriou. There's some evidence that this was actually had been developed before that. And but anyway, so we can basically adapt that algorithm into NBS, and we can end up with an algorithm that is going to do no more than 2 times the necessary node expansions. But as I said, we're going to assume we don't have consistent information about the consistency of the heuristic. And the idea here, well, let's start with the pseudocode. And so NBS looks something like this. So we're going to say put start and the goal onto the forward or backwards queue. Okay. And then we're going to say while the queues are not empty and we don't have a solution, then what are we going to do? Among the states on the queues, select the pair with the lowest LB, and I'll put lower bound just a minute to remind you what that is, and expand both. Okay, that's the important piece right there. And assuming when we do the expansion, we have some checks here. So I'm not going to go into the low-level details of these algorithms that are sort of the same. But if I expand states, then I check to see, did I find a solution in both directions, or did my 2 front twos meet? And if they met, then did I find a solution or not? And if I found a solution, there is some also testing to say, I have to show that actually that the solution is optimal. So if I have a given solution, I need to continue doing this as long as I haven't proven it. I have to keep expanding states until I've proven it. And so, but if we think at a high level, then this is what it needs to be done here. And I'll talk about termination in just a second. So if we look at A star says put the start on the goal, on the forward queue, and while the queue is not empty, then among all the states, you choose the state in the forward queue with the lowest F cost and expand it. And so what I'm going to say is select a pair of states with the lowest lower bound is the equivalent of my F cost in a bidirectional search. And then we're going to expand both of them instead of just one of them. Okay. And so now we have to talk about, well, what is actually going on here? How does this process work? What are some of the other details here? So just as a reminder, what is the lower bound? Lower bound is equal to the maximum. It's a maximum of 3 things. So G forward of N, some node N, plus G backwards of N, F forward, sorry, let me write this a little bit differently. G, so this is the lower bound between N and M. And so this is the forward G cost of N, the backwards G cost of M, the forward F cost of N, and the backwards G cost of M. Okay, so if I have a pair of states, I can look at these 3 pieces here. And the one thing that we're not doing is we're giving no front-to-front information. So here, F cost, this is like A star. But here, we potentially could put front-to-front information for NBS. We're not going to do that right now. Okay. And so this is equivalent. So remember, we take the max of these. And I didn't leave much room here. We take the max of these. And the idea is that if I have a pair of states, what the theory says, if I have a pair of states for which the lower bound is less than C star, LB of N comma M is less than C star, we must expand N or M. Okay. And so the idea is, okay, we've got these pairs. We're going to choose a pair of state with the lowest possible lower bound. We're going to expand that state, and we're going to continue that process until we've found and proven the optimal solution. And so what's actually going on here inside NBS is we start expanding states, and what we're going to have is we're going to have an estimate of what the optimal solution is. So the current lower bound, so the best lower bound is the estimate of C star. And so when I look at my best lower bound, that's my estimate of C star. If I have a solution that's less than that, then I have known, because if I think about my best lower bound, if my solution is less than that, then I know that I found the best solution, because there will be no states that have a lower bound less than that anymore, and therefore I can terminate. And so the question that I'm going to have here, is once I get my lower bound to that, the question is, well, how do I actually do this efficiently? Because what I need to know here is, how do I select the pair with the lowest lower bound? The simplest way to do this would just to be iterate through all pairs of states in the forward direction and the backwards direction, and ask the question, what pair of states has the lowest lower bound? But there's n squared states there, and so that's going to be a really expensive process. And so I don't really want to be able to do that in practice. And so how am I going to do this in practice? So what we're going to look at, and let me actually just show you an example here. So let's just put a box around here. This is MM and FMN. So that's all we're going to talk about here. So we say those are complete, do our little boxes around them. And this is NBS. So this is our NBS algorithm. It's telling us how we can do, how we can actually solve things with NBS here. And what we're going to want to look at is now just some examples here. Okay. So let's look at how we can compute the minimum lower bound. And what we're going to look at is an example here. And in our example, we're going to have 3 states. We're going to have basically an example where we have the same states in the forward and the backwards direction. So 8, 6, and 3. And what we have here is the H. So this is the G cost, is written inside here. And we're going to write the H cost outside. And so the H cost here is going to be 1, it's going to be 6, and it's going to be 10. And over here, the H cost is 1, 6, and 10. So we're going to ask this question, is which pair of states in this example has the lowest lower bound? And remember, lower bound is the sum of G, or F in the forward, or F in the backwards. So what I can do here is, well, we can just write everything out and look what happens. So what is the F cost? I'm going to write this in a different color just so we can see the calculation that's done here. So the F cost here is 9, 12, and 13. 9, 12, and 13. And then we can ask the question, between pairs of states, what is the G plus G cost? And so if I just look here, we won't write this down, but we see the G plus G here is 16. The G plus G is 14. The G plus G is 11. And then we have 12 and 9. And G plus G is 9 and 6. So the G plus G is lowest down here. And so if we ask it which one has, so these two have the lowest G plus G, but their F cost is highest. Okay, so if I'm asking what's the max, if I look at this pair of states, well, in fact, let's compute this. So we can look at this, for this state, for this pair, what is the lower bound? Well, the lower bound here is going to come from the F cost, which is 13, or G plus G, which is 11. And so this is 13. And in fact, if I look at any of these states, then 3 plus 6 is 9, but F cost is 13. and 3 plus 3 is 6, but the f cost is 13. So when we compare these pieces, for this state down here, the bound is always going to come from the f cost, and this state is going to have a priority, or the lower bound of this state, considering all other states, is going to always be at least 13. Now, if we look here, because the g cost is 8, so 8 plus 8 is 16, 8 plus 6 is 14, and then when you go here, 8 plus 3 is 11, but the f cost on this side is 13. So it ends up that if I think about the first state combined with others, so as I said, 16, 8 plus 6 is 14, or here we get the 13, we also see that the priority of this state here combined with any other state is also going to be at least 13. So this state, which has the lowest f cost, is not necessarily going to have the lowest priority, and this state, which has the lowest g cost, is also not necessarily going to have the lowest priority. However, when we look at this pair of states here, and let's label them here in a different color. So this pair of states here have lower bound is equal to, well, what is it? Okay, f cost is 12, and g plus g is equal to 12. And so, and f cost is 12 here, so lower bound is equal to 12. So the state that I actually want to expand in this state space, or the pair of states that have the lowest lower bound, are not the ones with the lowest f cost. They're not the ones with the lowest g cost, but there's these states in between here that are in between, and that's actually the state that NBS wants to expand next. Okay, and the question is, well, how in the world do I do this? And it ends up that there's a way we can do this efficiently, and we're going to do this with a set of data structures. So remember what I said in NBS here, and we didn't draw this out explicitly, but we need this estimate of C star. Okay, so C star is an estimate of the best solution so far. And so what we're going to do is start with an estimate of, like, for instance, C star is equal to 0. And then I'm going to describe some data structures which are going to allow us to not only get an estimate of C star, but they're also going to allow us to efficiently compute what pair of states have the minimum f cost. Okay, so let's take a look at that and see how we can do this. And so we're going to have a two-tier set of data structures here. The data structures we want is we're going to have something up here which we're going to call this to be weighting. We do this both in the forward and backwards direction. And then we're going to have another set of data structures down here, which we're going to call ready. Okay, and the idea here is we're going to sort these, sort by f cost. And then down here, we're going to sort by g. And this is going to be low to high. Okay, and the idea here is that if we think about our conditions up here, we have three conditions. We have to have, if we're going to expand it, then we have to have the forward f cost has to be less than C star. We have the backwards has to be less than C star. And then we have to have g plus g is also less than C star, because that's where we get our necessary expansions. So we're going to be estimating C star. And what we're going to do is we're going to start by putting states into the waiting list. And when we do this, they're sorted by f cost. We're going to get the minimum possible f cost. And the minimum possible f cost in both directions, ignoring g, is already going to give us an estimate of C star. So for instance, if the best f cost on one side, we look over here, the best f cost is 5, over here the best f cost is 7. Actually, this already tells us, because and here we actually know that if we're going to be putting states in here from low to high f cost, there's a few details I'm not getting into here, but if we go in here and we have in this case, well, let's assume for a second that the heuristic is monotonically growing, then what's going to happen is my f cost is going to be going up here, as the F cost goes up, then what happens? Well, F cost goes up, then my estimate of C star is going to go up. And so from the minimum F cost, either on these sides, we're actually going to get an estimate, as I said, of C star. Now, if it's 5 on this side and 7 on this side, well, we've got to combine states from both sides, and we'll take the max. Then we actually already know that the solution is going to be at least cost 7. And when that happens, what we're going to do is we're going to take all the states that have F cost. So let's just say right here that I know C star at some point is going to be greater than or equal to 7. And so 7 is my lower bound. It's going to be my current lower bound on the F cost. And so what I'm going to do here is take all states which have F less than or equal to 7, and I can put them onto the ready list. So F less than or equal to 7, they're going to go down onto here, and I'm going to get a bunch of states that come down onto here. Okay, so these states that are down here have already met the requirement of F of n and so F in the forward direction and F in the backwards direction. So these are the forward, and these are, for instance, the backwards direction. We know that they're less than our estimate of C star. And then the third condition we have to check is whether G plus G is less than C star. So what we can do now is we can take the best nodes off of each of these priority queues, and we can compare them. And remember, we're sorting them from low to high G cost. So if I take the minimum G from here and the minimum G from here, and they add up to something less than C star, then that is a pair. In fact, because I have the lowest G cost and I have an estimate of C star, then I know that is the current state with the lowest possible lower bound. Because I know all states in here are, if C star is greater than or equal to 7, then I know that C star is 7 or less for all the states that are inside here. And then I know that G plus G is going to be less than or equal to 7. And therefore, this is going to be a pair of states with the lowest possible lower bound. So what I'm going to then do, so I have this data structure. I'm going to put all my states into this waiting queue. And then I'm going to update my estimate of C star according to the F cost on here. And in this case, I look at both of these, and actually I take the maximum of the minimum. And then I'm going to take all the states that have that value, and I move them onto the ready queue. And I move them all onto here. They're all on ready, and they're waiting. Now so here they're waiting to be considered, to be shown that they're within the C star bound. Then they're going to move onto the ready list to say, now I'm ready to expand these states. And if I'm ready to expand these states, I look at the minimum G plus G. If the minimum G plus G is also less than my estimate of C star, then I can go ahead and I can expand those states because they have the lowest lower bound. And so I'm going to expand those states. Again, I'll put their successors up onto here, and I'll continue this process of moving them down onto ready. And now what can happen? Well, I could get to the point where the minimum G plus the minimum G is actually greater than my estimate of C star. So in this case, these are the states that are basically estimating C star is equal to 7. So what I'm going to say is, hey, maybe I'm going to exhaust those states that are estimating C star 7, and I'm going to update C star now to be 9. So because there's no more states up here with less than or equal to 7, and there's no more pairs of G cost down here that are less than or equal to 7. And so that would cause me to update this estimate. I would update this estimate to say, well, maybe my C star now could be 9 if that was my next cost. I continue now to move anything with F less than or equal to 9 down onto this ready list. And then I continue to expand as long as the sum of G costs is less than or equal to 9. Okay. So this may be a little bit complicated, but the idea here is that we have all the states that I could possibly expand sit up here on a waiting list. And once they're potentially at least as good as the best possible solution, so in this case, F less than or equal to whatever my current estimate of C star is, then I move them onto the ready list to expand. And that means that we've met the first of these two conditions here. And then I'm going to use this list by just comparing the first states on this list with the lowest G, low to high G. And I'm now going to expand these two in pairs. I take the lowest one of each of these, I expand both of them, and then I put their successors onto the waiting list, and then continue to move them down. So by that process, what you see is I never have to compare everything over here against everything over here. But the idea here is that I can filter the states with f cost because these don't depend on looking in both directions. So I can filter them with a single priority queue in the forward and backwards direction. Okay, so I filter these without having to compare front to front. And then when I compare front to front here, I'm wanting to start with the low values and work to the high values. So by doing one sort here and one sort here with a regular heap or something like this, then going from low to high here does not again require front to front comparisons. I can simply looking at all pair front to fronts, I could simply look at the single state which is lowest on each side and sum up those G costs to see if it's less than my current C star. So the way the NBS works is it has an estimate of C star. Anything that is that estimate or less goes on to this ready list here, and we'll continue to expand those states as long as they're states that have a lower bound, which is less than or equal to that current estimate. When all of those states have been exhausted, we'll increase to the next possible estimate. We'll bring the states off of the waiting list back onto the ready list, and then we'll expand any states that are available there. And we repeat that process as this estimate goes up and up. As the estimate goes up, then eventually it reaches C star, and when it reaches C star, then the states will come off of the waiting onto ready, and we'll then be able to expand them. We'll find them on the ready list and be able to find the optimal solution there. Okay, and so overall, if this question of like how do I select the pair with the lowest bound is an easy thing to do, so if I can do this efficiently, it doesn't require n squared time, then this process is fairly straightforward, right? We just continue to raise our estimate of C star, and until I found a solution which is equal to or less than the current estimate of C star, I'm just going to expand the lowest lower bound, expand the lowest lower bound. And what's interesting here is it's not the state with lowest G cost, it's not the state with lowest F cost, but it could be something else in between. And we'll basically raise those costs up. And what's going on here is we're expanding all of the necessary states because we're expanding them in pairs. We're doing no more than twice the minimum number of necessary states. And then of the states that are not necessary, we can't say very much. And those are the states with the lower bound equal to C star. And so there's some tie-breaking rules and other things like this that can be helping to do this more efficiently. And this also depends maybe on the domain that you're in. Okay, but what this is this is sort of a first algorithm that maybe is in should be in our modern queue of algorithms we want to think about, that is going to be thinking about as a star about the minimum number of node expansions that I need to do. The algorithm overall is based on this principle of looking at the problem as a minimum vertex cover problem and directly trying to solve that minimum vertex cover problem, and not necessarily thinking about the guidance of the heuristics explicitly. It's happening implicitly, coming from, of course, the F costs and the G plus G here, but it's not explicitly saying, oh, I want to be guided by these costs. We're actually guided by this proving process, trying to prove that the path that we can find a solution, or proving what the optimal solution is, and expanding everything that is less than that. So this is a high-level overview of the algorithm. There's a number of additional details here that would be required to implement this, but it's something you can implement you could even implement in a very naive way by actually just going over n squared pairs, and then you'd be able to get this to work. There's some details here. You want to make sure that you never re-expand states. So this process does allow me to do this. So never re-expand states by any other means. I wouldn't want to be sorting by others, like when I tie break, by finding the lowest G here, it means that I can never find a shorter path to a state that's been expanded. When the F cost goes up, then the G cost is never going to get me. So I always do low G cost to high G cost. I can't find a shorter path to another state that's already been expanded. This is analogous to what happens in A star. So again, I'm not going to go through some of those proof details, but NBS has this guarantee: no more than 2 times the necessary expansions. and necessary expansions, meaning those with LB. Sorry, I always like to put my B first. LB less than C star. And we don't say anything about tie breaking. And what we're going to look at in the next video is we're going to look at what happens if we go here and try to add some front-to-front information. What additional front-to-front information can we add? And how can that front-to-front information allow us to actually be able to find, to be able to prune states out of the search process, to be able to show that we have additional, because we know that the heuristics are, if we know the heuristics are consistent, do we have additional information we can put right here that allows us to be more efficient in practice? But this gives a sort of a brief high-level overview of how NBS works and how we can build data structures that allow NBS to run efficiently.